I want. I was thinking materials, but I think I'll do electricity as the next topic instead. I think I'll do electricity, yeah.
But maybe electricity is hard.
No, I'll do electricity next, yeah, that's what I'll do.
Okay, so it's easy, yes?
It's okay. I mean, what exactly is meant by easy, you know? The good thing about physics is that the difficulty doesn't increase, unlike maths. As you know, in maths,
Yes, math
it gets harder, more and more and more. Yeah.
Because it's harder.
And some probably chemistry too. But at least with the physics, the difficulty stays about the same. In fact, it, in my opinion, is a little easier after the mechanics because the topics aren't as big. So, you know, I think that is an advantage. So we are going to start electricity. So this is, if you remember, I said for the physics, there's six parts of the course. We finished part 1, the mechanics, so now we're on to part 2. I'll do next is the electricity. So let me just start my pen. And we'll probably get 2 lessons done because there's no homework to go through. Okay. Right, so charge and current. Sorry, do you have this? Charge and current. Yeah. Okay. Right. Now, from chemistry, or even just basic middle school knowledge, you understand that there's the thing called electric charge. And it's usually, or not usually, it's associated with electrons. So electrons, we say, have a negative charge. Yeah. And protons have a positive charge.
And negative.
The neutron has no charge.
Yes.
Yeah. There are other things that have charge as well, yes. Not just electrons and protons. But for us, it will just be electrons and protons. Electrons are negative and protons are positive. This you all know, or you should know. So things that are negatively charged and things that are positively charged attract each other.
Yes.
This makes electrons and protons stick together. Mm-hmm.
Because there is like some magnetic thing that
well, like a magnet, yes, so they stick together then. Yes. Things that have the same charge push each other away. They repel. This is called the law of charges. So you might just want to write this name down. I think you know it already. Law of charges. For me? Yeah. I need it? Oh, I didn't even notice that happened. Japers. Alright.
Okay.
What does Lorraine give it any name in chemistry, or I mean law of charges, or is it given any special name in chemistry?
No, I think we did not take it now.
Well, you understand the idea in chemistry, yeah.
Like charges, each other, like charges attract.
Yeah. Now, you don't have to write all of this down because you know it.
But,
law of charges is its name.
In electricity, I know something that I took it in the school.
Yes.
There is the electric bulb, how the electric being transferred.
Yes, we'll do all that. Don't worry, we'll do all this. Okay, continue? Yeah. Okay. So, this is the first definition which you might not have. An electric current is a flow of electric charge. So, I don't know. Did you do that with Lorraine, or? No, I don't. Probably there's no reason to. I don't think. So if I kind of draw it, you have your, oh dear, oh my goodness, okay. Imagine you have this electric charge, it's negative, and let's say it's moving this way, then we call this an electric current. Yeah. Now each of these are called electric charges, but when they move, we call it a current. Okay, so charge is one, and current is when they move. Like a river current, you know.
Like something moving.
It has to be moving. If it's moving, we call it a current, electric current. Okay, do you have that vocabulary? Yeah. You know current for water, don't you? Or not? No. In English, when we talk about a river current, we mean the flow of the water. This is a new word? Yeah?
Well,
kind of.
I mean, we have heard about current in the electricity, you know, relative to electricity, but not when it comes, like, the way you are saying it.
For water?
Yeah.
Oh, interesting. Interesting. I would have thought the other way around. Okay, so you can use it for water as well. Continue? Yes? Right. In a metal, it's the free electrons that flow. So you know from chemistry that there's free electrons in a metal. And this is what flows when you have a current. So here's just a little picture of it. These are all the electrons moving in a copper wire or something like that. Yeah. I don't think you have anything to write down there. You did this with Lorraine. What do you call in chemistry? Sea of electrons or
Mobile.
Sea
Sea of mobile electrons.
Sea of mobile electrons. Yeah. So they can flow. They can flow. Now, an electrolyte. An electrolyte is a chemical that conducts electric current. So one way you can have a flow is if you use a metal. But another way is if you use a special chemical called an electrolyte. Okay, did you write that down?
Yeah.
It's often used in batteries to make ions flow. Now you've done ions in chemistry, haven't you? Yeah. So ions have a charge. So in an electrolyte, it's the ions that move, that carry the charge, which makes the current. Ions are just atoms with an... Oh, you know what ions are, don't you? Yeah. Yeah, so you don't need to write what they are. So in an electrolyte, the ions move. That's all you really need to know. If the atom has an extra electron, what charge will it be? Negative. And if it's missing an electron, it's positive. Yeah.
So which one is anion and cation? I'm always confused.
Yes, even me.
Cathode?
No, cation and anion.
I think. See, that always confuses me too. It's not something that we usually do. The cat one is the minus one, and the way I remember it is that cats are bad. So this is how I remember it.
Because before I had a cat and it was not funny cat, so
Yeah,
I
exactly.
put it away.
Yeah, minus cats. Yeah. Okay. Yeah. So here's an example here. If you can see, don't draw it just yet. This is Zn. You know Zn?
Zinc.
Zinc. Yeah. And Cu. Copper. Yeah. And what happens here, the negative
goes to the zinc.
what's it, SO4,
Yes.
sulfate, yeah, and Zn
And
zinc.
goes to the copper.
Oh, sorry, I should have said what this is H2SO4. So, yeah, sulfuric acid, yeah. So this is the electrolyte. And you have the ions moving through the electrolyte. So the negative one moves this way, and the positive one. Now, we don't do this in physics. This is more of a chemistry thing. So we don't have to worry about this. But I just wanted to show you an example of an electrolyte. The negative will move to the zinc, the positive will move to the copper. And what happens is the copper will start to change colour because the zinc starts to build up on it. I think these change colour, don't they? And in fact, if you leave this on long enough, this will start to get a little bit bigger, I think, and then this one here gets a bit smaller. I don't remember. We don't usually do this in this physics class. Yeah? Or is it the other way around?
So on the copper, the zinc plate will be
Yes.
the zinc will be covered with a.
But the copper builds up here.
No, on the copper, the zinc.
The zinc builds up here. Yeah, okay, yeah. In fact, it doesn't matter for us. We don't need to know it. I just wanted to show you that you can have the charge flow through an electrolyte. This is an electrolyte here. But actually, this is how you make batteries.
Yeah.
You know, this is how you can make a battery. And this will keep happening until there's too much built up on it. It'll change colour and it'll be like brown or something, and it won't work anymore. But anyways, we don't need to worry about that. That's not something on this course, but I wanted to show you the picture. Right, so which way should we say the current flows? So here's a picture, and here's a battery. Can you see that?
Yes.
Here's the bulb, and here's the switch. Do we say the current flows from positive to negative, or maybe we could say negative to positive?
Negative
Positive to negative, I think.
Negative to positive.
Yeah, okay.
Maybe from left to right.
Left to right, right to left?
Either way.
Either way, both ways, none, not your way?
Negative to positive.
You think it's negative to positive?
Yes.
You are wrong.
Ah.
Now,
Positive.
yeah, now it's actually a little bit complicated. So when I draw a positive here and a negative here, like on the battery, let me draw my battery. So here's my battery. This is the positive side, this is the negative side, and here is the current. So we say it flows from positive to negative. This is the way we draw it. Tell me this now. Actually, the flow is from positive to negative. So, what do you think that means? The electrons that are moving in the metal, these are moving. Which way are they moving? From positive to negative?
Yes.
No.
Why?
Negative to the positive.
About how?
No, this is what the problem is. We say the current flows from positive to negative, but actually the electrons are actually moving the other way.
How, like coming back?
This is what you meant.
Yeah.
Yeah.
My teacher says it's negative to positive.
The electrons, yes.
Yeah.
The electrons.
Yeah,
Electrons move from negative to positive, but we say the current flows from positive to negative. Now you might be thinking, but that's stupid. Why don't we say negative to positive for both of them? Like, why is it different here? It's really annoying. So you have to be very careful. The electrons flow negative to positive, but we say the current flows from positive to negative.
Can we draw it and draw this?
I think I might have a picture here. So yeah, if you look here, the current goes from positive to negative, but the electrons go from negative to positive.
Like if there is a current, so it will be moving from positive to
Yeah,
negative.
if there's a current, we say it's from positive to negative.
But if there is a flow of electron, it will be negative to positive.
Always.
Yes?
Yes.
Yes. It's easier.
Well, I don't think it's easy. It's annoying is what it is.
Like, no, but it's like, it's for me, like, it seems like easier.
As you wish. Did you see this in high school before?
Yeah,
Yeah,
it's a big topic of electricity.
Yeah. Okay. So just please be very careful about that. It's a pain, but you have to remember it. Yeah? You got this? Yeah. Yes? Yeah. Okay, continue.
Yeah.
Continuing.
Yes,
Yeah. So if an electron moves from A to B, we say there's a current flowing from B to A. Yes, B to A. That's right. Okay. So why? Why might you think this? And the reason why we have this weird situation is because we call electrons negative. This is the reason why. In fact, it would have been better if we said electrons are positive. Now you might be thinking, but electrons are negative. How can we say that they're positive? But it does. Let me give you an example. This hand, is it left or right?
What?
This hand, left or right?
Left.
This hand?
Right.
Now imagine tomorrow we change the meaning so that right is left and left is right. We swap them, okay? So now I say this is my right hand, this is my left hand. Go down the street and turn right, then turn left. If everybody makes the change in the name, does it change anything? Not really. It's just a name, left, right. Positive and negative is just a name as well. We call the electron negative and we call the proton positive. But we could have said the electron, we call it positive, and the proton, we call it negative. And in fact, if we did that, then we wouldn't have the problem we had in the last slide. The reason it's like this is because the names are the wrong way around. Okay? And this is because of Benjamin Franklin. You can read that comic later anyway. Do you know Benjamin Franklin?
Yeah. Light experiment.
One of the first people to do experiments with electricity. The problem with electricity was when people first studied it, they weren't sure what it was. So the name that they gave to one thing was negative and the other thing positive. But it's only later that people realised it would have been better to call it the other way around. So it's too late now. It's too late now to change it. Just like it's too late to change left and right. So this is just the unfortunate situation. Okay, so now on to some units. Have you heard of this unit before, the amp?
Yeah.
Yeah, you know about amp, yeah. We mentioned amp, yeah. Now, the definition of amp is very, very technical. Very technical. Yeah. I is it, yeah. 1 amp is the current provided. Okay, so actually just before I go on to do that. So let's imagine that there's a current here of positive. And there's a current here of positive. If these are both positive, what will happen? Will they try to move together or move away? They'll move away. So there'll be some force, there's going to be some force here.
But if such one positive, one negative, it will be attractive.
Yes, but just focus on what I'm doing. Positive and positive, okay? So this is 1 amp and this is 1 amp. So we have 1 amp if we have this much force. So if the force is 2 times 10 to the minus 7 newtons, then we say we have 1 amp of current. Now the definition, it's not an easy definition. It says 1 amp will produce an attractive force of this per meter in 2 straight parallel conductors. The definition is very complicated, but the simple meaning of the definition is if you have 1 meter and 1 meter and the force is this much, then we say we have 1 amp. But like I said, this is a very difficult technical definition, and they've never asked it in the exam, ever. So don't stress about remembering it perfectly. In fact, even if you just remember this number and you can draw this picture, I'll be happy. Okay? Well, draw the picture and write this down.
The way you are saying the definition, it's a bit easy than this one.
I know, but this is like the textbook technical definition. But it's more important for me that you can understand the meaning here. So if you can write this ugly definition down, please. Oh yeah, and actually what I didn't say, which is in the definition, is that that they're also 1 meter apart, of course. If I had this question in an exam, what I would do is draw the picture and then try to write the definition down.
If I do it in my own language, it would be...
You get the marks for what you write in it, not the picture. I would just use the picture to help remind me.
If I write the definition with my own language, not like...
Oh, I understand. Yes. Yep. There's a couple of key points to get in your definition. You definitely want this number, and also that they are 1 meter apart as well.
What does negligible mean?
Whereas a negligible circular cross section means that the thickness of the wire is too small to be important. You can forget about it. In other words, it's a really, really fine wire with no thickness. Yeah. Yeah. You got that? Can I go to the picture?
Yeah. No.
Not yet? Yeah. Is anyone doing electrical engineering next year? That's you, yeah. Oh, the two of you.
No, I'm not. I will do it.
Okay, all right. Electrical engineering, you're doing that next year, yeah. Yeah, so this will be an important one for you. Continue. Yeah? Okay. Now, if you want, you can draw the picture. It's ugly, but you can try and draw my picture.
Okay. The picture is easier than the definition.
I never remember this number because the only time you use this number is in the definition, so this is why I never remember it. Okay, continue. Yeah. Right. Oh, look, there's a nice picture. Forgot I had that there. So you have 1 meter, 1 amp, and it will make this force. Now, I don't know why they drew the arrows this way.
Yeah.
Oh, I know why. In the experiment, what you do is you put a special clamp here and here, and this clamp can measure. You can measure how much force you need to keep the wires together to cancel this one. Do you know what I mean? Like imagine. I'll make it simple. This will want to move left and this will want to move right. So if I want to stop it moving, what I could do is something like put a string here and a string here, and then put a small weight here. Yeah, and if I can balance the wires, then I can see how much force I need here and here to cancel this one and this one. You know, so that's why the arrows are drawn inwards here in the picture. Okay. Now, the Coulomb. Have you heard of this unit before?
No.
See, you don't use it in chemistry, but you use something similar to in chemistry. It's for measuring the charge. Yeah. It's an SI unit for charge. So the Coulomb is the International System of Unit of Electric Charge. Yeah. Got this? Yeah, yeah. Now, the definition is actually pretty easy. It's the charge when you have 1 amp for 1 second. So, imagine we have our conductor and there's a current flowing through it and it's 1 amp of current and we have this for 1 second. Then the charge that we get will be 1 Coulomb. So 1 Coulomb is 1 amp for 1 second. So that's a pretty easy definition. So as a formula you can write it like this, that the charge equals the current multiplied by the time. Q is the charge, I is the current, and T is the time. Now wait, before you write this down, I'll just tell you that this definition is a common definition in the exam. They like asking this one because it's easier, okay? So you might want to make some notes saying a common exam definition, a Coulomb. Okay, now you can write it down. Yes, but why do you always sit in the corner though?
Just so I can see.
You can't see there?
No, I can see. Like,
But what?
like I like to sit with someone, so if I did not understand things, you can
Okay,
explain to me.
but you realise there's other people that are not in the corner you could sit beside.
Okay, but if
You
I
don't
can-
like him? You don't
No.
like him? No? Come on. Next, I don't think I'm going to let you sit in the corner anymore. I think I'm going to ban it, okay?
Okay.
This,
Yeah?
the current is L,
I.
I,
That's an I.
oh,
Yes, that's a current. Okay. You have this?
Yeah.
Yep. Andy? Not yet? Yeah, okay. Yeah? Go on? Okay. So finally, how big is finally for this, how big is 1 Coulomb? In fact, it's really big. A Coulomb of charge is a lot of charge. It's a lot. Really, really big. Because, for example, an electron has this much charge. Minus, because it's negative, 1.6 times 10 to the minus 19 coulombs. So a coulomb is a really, really big unit because an electron has this much charge. Okay, so coulomb's a big unit. And of course a proton would have the same charge except with a plus instead of a minus. Often, because this is common, we write it as E. So E represents the charge of an electron, or really I should maybe say minus E maybe, but anyway, it doesn't matter. E, or in chemistry, what do you call the charge of an electron? Yeah, go on, don't be shy. No?
No.
No, you do.
What?
okay,
In chemistry,
What?
Lorraine would say, this electron has a charge of... -1. Wouldn't she? No. Wouldn't she say like a proton is +1 and an electron is -1?
yeah,
If we are saying plus, that's usual, that is +1.
Yeah, but now what I'm saying is, would Lorraine say this proton is a +1 and this electron is a -1? So she might say something like, you have a proton, and an electron, so the charge in total here will be a +1 charge.
Yeah.
Would she?
yeah.
She would say that or not? You look confused.
Well, yeah, I get it, but no, not really. She didn't say that.
Well, what would she say then?
No, we
Nothing like
calculate the charge of like
Yeah,
an ion.
calculate.
Great, so what would the answer be? Give me an example.
For instance, vanadium +3.
That's what I mean.
Yeah.
So that +3 means you're missing 3 electrons. Yeah. So the charge is +3 but I'm putting it in quotation marks because it doesn't have any units. +3, but there's no units.
Yeah.
So what I'm saying is the unit for -1 is this. Or +1 would be this, but a plus. I think it's worth writing that down. So this is how you can compare the chemistry with the physics. This is the unit we have for -1. Yeah? You got my idea here? Yeah. Yeah?
Yeah.
Yeah? Okay. Continue, Andy? One sec. Okay. What are you doing in chemistry at the moment? Or did you have class yet?
No.
Not yet. When's your first class then?
No.
Oh, right. You had your test though?
Yeah.
Yes, okay, yeah. Alright. Andy? Yeah? Okay. Right. Let's have a look. There's only one question to do because there's only one formula. So we have a 100 milliamp current flows through a copper wire for 2 seconds. What is the charge? Alright, so let's do this one together. The formula is Q equals IT. Or if you want, you can write delta Q, but you don't need to. Okay, so what is the I?
I is
100
Milliamps. So this is 0.100. 100 milli. And what's the T? Time, which in this case, 2 seconds. So the answer is 0.200 coulombs, or if you prefer, that's 200 millicoulombs. And that's it. You look a bit confused.
Why we have to write a row after two?
I don't know why I did that. I'm sorry. I don't know. No, you don't have to. I think because Furong, I was thinking of 1000 milli equals 1. So this is why I wrote it like this. Because in my head, I was thinking of doing this next.
Okay.
Yeah.
Okay, tell me one thing.
Yes.
100
Milli.
milli. So it will be multiplied by 10 minus 2.
Oh, you do that again. 10 minus 3. You
I-
keep saying 10 minus 2 for
I'm
milli.
really confused in this conversion of the unit.
No, okay,
Most of the time.
look. I is 200 milli. And how big is milli?
It's multiplied by 10 minus 2.
No,
Minus 3, minus 3, minus 3. 10
three.
is 2, yeah.
2.
Yeah.
Right. So this will be 400. Oh, sorry, it's not. Oh, wait, is it 100 or 200? 100. Sorry. 100. So this will be 200 times 10 to the minus 3. Yeah. Which is 200 milli
Okay, I want
coulombs.
to ask one more
Yes.
thing.
Why is
How
this
do we know?
confusing? Yeah.
How do we know that when we have to multiply or divide?
But here it's 100 milli amps. So this is 100 times 10 to the minus 3. So it's multiplied.
Okay, if sometimes we also divide.
Yeah, but I suppose, if it was 1 over 100 milli, but you're still multiplying here.
No.
I know what it means for divide when you're converting the unit.
Yeah.
Yeah, but that's when you need to convert from one unit to another unit, which.
From kg to gram.
Yeah. So
Multiply or divide. We
no,
divide.
you're thinking about it wrong.
Okay,
You
okay.
see, yeah.
Can I say?
Go on.
If you do it by the scientific times 10 to the power of something, you multiply in both cases. It's either the plus or the minus that makes the difference.
Yeah, but I know what he's talking about for the dividing one. You
The
want to
dividing is
you want, for example, you want something like
2 kilograms.
2 kilograms into grams.
Yeah.
Now, I know why you're thinking this because of high school, okay? So I need to try and get this out of your brain, all right? Because you're thinking in high school, my teacher said to convert from this to this you multiply, and from this
Yeah.
to this you divide.
Yeah.
You need to delete this memory. Delete it, okay? This is not the way to be thinking about it. So for example, if you want 2 kilograms into grams, how big is a kilo?
100.
1,000.
1,000.
So this is 2 times 1,000 times gram. Okay? Now wait, that's okay, is it?
Yeah.
Now let's do it the other way. Let's say you have 2,000 grams and you want to make it into kilograms.
Yeah.
Do you have a kilo here? No, there's no kilo symbol present, is there? So if you introduce a kilo symbol here to make it kilograms, you must balance it by dividing by kilo as well.
Yeah.
So you have 2,000 kilograms divided by 1,000. So that is 2
Yeah.
kg.
Yeah.
Or we can do it like 2,000.
No.
2,000 multiplied by 10 minus 3.
No. Don't do it this way.
Okay.
Just do it this way. Yeah?
Okay.
Now, I know why you're saying what you're saying, because that's how most high school physics teachers explain it. But I find this is so not helpful for more difficult problems. You know? So you really need to delete that from your mind and think about conversion being done this way.
Yeah.
Yeah?
For sure.
Yeah? Okay, continue. What? What's wrong? No, what's wrong? 1 or 2, what's wrong?
Yeah.
Wait, are you happy that this is this? So the answer here is 2,000 grams. Happy? Okay. Are you happy that this is the same as this? But this and this cancel.
Why we have to do that?
Because in this question I wanted you to convert to kilograms.
But gram to kilogram is 1,000.
No, well, yeah.
It's minus.
Multiply 1,000. Is this what you mean? Multiply 1,000?
Divide.
You see, you're thinking about it the same way he's thinking about it. This is
easier.
no, don't. Okay, but it's much. Trust me, please trust me. It's much better for your future in physics if you think about it this way.
I think this way is difficult.
You must trust me, okay? You must trust me on this, please. Yes.
When we convert into centimeter square, we multiply by
Centimeter squared is a bit weird, but yeah, for example, if you have 100 centimeters squared and you want to make it meter squared, yeah? 100 centimeter squared. Now, how big is centi? 10 to the minus 2 meter squared. So this is 110 to the minus 4 meter squared when you put the power in, which will be, what will that be? 0.01, yeah, meter squared.
Okay, but
And then it's the other way around, yeah? So like, for example, if you have, let's say 1 meter squared, but you want to make it centimeter squared, yeah? Do we have centi? No, so I'll need to put a centi on the top and on the bottom. But I don't put centi, I actually want centi squared. These still cancel to make the original.
So it will be 1.
So it's still 1 meter squared. This is 1 cm squared over c squared. This will be 1 cm squared, and centi is 10 minus 2 squared, which is 1 over 10 minus 4,
10,000.
which is 10,000 cm squared. Okay, so this is my point. It's much better for you to think about the converting like this instead of, oh, what do I do? Is it 1,000? Is it 100? I can't remember. What did my teacher say? It's better if you think of it like this, as an algebra problem. Yeah.
But next semester or the first semester, we will not take geometry, yes?
What are you talking about? Just write this down. Just write this down. Can you put this in your mind to replace the original?
Okay, I
Yeah?
have one more question.
Yes.
When it's kg,
Yes.
meter,
Yes.
and
No,
then
stop.
minus
No, stop. Are you going to say kg and meters and then replace it with grams and
No.
Okay. Well, yeah.
when it's meter minus cube, and
Yeah.
then we have to convert in centimeter minus cube.
It's like this one.
It's same.
Same method. Yeah. So like you have meter cubed
Yeah.
and you want centimeter cubed,
Yeah.
so you have to put in a centi cubed.
Yeah.
But you must put one on the other side to balance it still.
Yeah.
So if you put a centi cubed on the top, bottom, then you must put one on the top.
Ooh.
Yeah, okay, now
Yes, 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 yes.
get that burnt into your brain, okay?
No.
Replace the original.
It's saved.
It's saved? Okay, fine. I hope so. Okay. Now, let's have a look here. So, these questions aren't that difficult because it's only the first lesson. So, in fact, I think you could probably do these,
No.
well, maybe, yeah, definitely. It'll only take you like 4 minutes to do, and we'll do the answers together now. So, if you can try these questions.
So time needs to be second. You might as well stop the recording since you're only writing it.